Good afternoon. I came here to talk about a project I've been working on for this year, basically, and even slightly before that. And that is allowing GCC to compile OpenMP 4 constructs for heterogeneous systems architecture. My name is Martin Jambor. I am a toolchain engineer at SUSE Labs in Prague. And well, just like everybody here, we've been thrown into the heterogeneous world. Before that, I was a classical compiler optimization engineer worrying about shrink wrapping, constant propagation, inlining, things like that. But I've been asked to provide support for compiling for HSA. I will talk about that in a moment. And I've been quite surprised, even though I obviously knew one or two things about it, just how big heterogeneous computing is about to be. And I probably do not have to explain this to you. I reckon that most of the talks, at least at the OpenMPCon, do relate to heterogeneous computing and GPUs and the new era of computing in one way or another. What I would like to point about, because I want to introduce HSA to you as the first thing in my talk, is that when people talk about heterogeneous computing, they usually mention two problems. One problem is access to memory and the fact that in heterogeneous systems, the different components have either different memories or they have very different views of the memories. And the second problem that is often mentioned is that the heterogeneous devices have very distinct, even the same kind of heterogeneous devices, have often very distinct programming models. Their ISAs change very often, so if you now compile for a special ISA, that ISA may not be usable. That may not be usable in the future because future GPUs, for example, may use different instruction sets and so forth. And that is the reason why a few companies, such as, well, first and foremost AMD, but also ARM, Texas Instruments, and many others, have come together and decided to work on heterogeneous systems architecture that will solve these issues. And so my first part of my talk is going to be a very, very brief overview of some of the features of HSA. If you want to know more about it, if you don't already do, then please do go to hsafoundation.com, where you will get all the specs and a lot of additional material to have a look at. But the two features that aim to solve the two big problems with heterogeneous computing is that first, the CPU and GPU have not only access to the same memory, the system DRAM, but they even are able to use unified virtual address space. So the part of the program on the CPU can pass a pointer to the part of the program running on a GPU, and the GPU part of the application is able to grab the data and work on them. And so this has many implications, and first of those implications, of course, is that we do not have to do any DMA transfers. We don't have to do any very expensive memory mappings when working in HSA. But that's not the only implication that there is. The second feature of heterogeneous systems architecture is that it is being programmed, or at least the GPUs within that architecture, are being programmed in something that is called HSA intermediate language. The intermediate language is an intermediate language, which means that it needs a finalizer to be translated to the final ISA whenever you actually want to run the code, which brings some overhead, but it has the advantage that the code that you compile now into HSAIL will be runnable on future GPUs in years to come. And you will not have to redistribute a special version for your code to for each particular GPU that you want to have run it on. The intermediate language is very close to the assembly language, which is on purpose so that a finalizer has an easy job. It has, however, very, very many registers and some other optimization features. And one feature that is, of course, typical for a GPU programming environment is that it is explicitly parallel. Well, let me actually go back. One slide. This is an example that does vector copy. As you can see, it does not have any loop in it. And yeah, well, the reason is that it is explicitly parallel. I suppose that many of you have direct experience with programming GPUs, so I'll go very, very quickly over this slide. But in one way of thinking about explicit parallelism is that GPU runs very, very many threads, and each thread runs one iteration of the loop. HSA has support for three dimensions, for three of the iteration space in which each of the threads then run. So on this picture, which is one that I stole from the hsafoundation.com website I told you before, is we can see a representation of a workspace grid where each of the tiny boxes is one thread that is executing its portion of the iterations, 3D iteration space. And the iteration space itself is not only partitioned into individual threads, but it is partitioned into work groups, which are portions of the iteration space within which the threads can communicate. They can synchronize, and they can also have, each group has its shared memory, which is available to the threads within the group, but not outside of the group. And then a part of the threads run in parallel. They execute the same in lockstep, which means that they execute the same instruction, but on different data. As you can see, the wording that is being used in HSA is very similar to OpenCL. So we do, one thread is actually called a work item. We don't have gangs, we have work groups, and so forth. So now let's leave HSA and talk about what we've been working on, what you need just in case you liked my talk and wanted to experiment with what we've done. Our work, we're doing work in public. We do it on a branch of the GNU GCC compiler. So if you're interested, you can just use either the Subversion or the Git mirror, and within a few months, hopefully, the whole GCC project will switch to Git, so then you will be, there will be a new address, but you'll be certainly able to figure it out. And grab an HSA branch and have a look at it. In order to run your code and even compile the compiler, you will need a few more things, though. First and foremost, you will need HSA runtime, currently available only from AMD, which is available at this GitHub address. Now, the problem with the AMD runtime at this moment is that this Wednesday there has been a new version released, which is, on one hand, great news, because we've been depending on one feature that's been brought about by this new release, specifically dynamic parallelism. At the same time, since Wednesday, I've seen some performance regressions. I've seen some finalizer seg faults. So we are currently, at the moment, in a state where things need to settle a little bit. The new runtime needs it needs a patched kernel, unfortunately. The previous runtime would work well with the reason for the with a recent release candidate kernel actually, but you need and by kernel I mean Linux kernel, because yeah, I'm from a SUSE Linux company, so pretty much none of what I'm talking about applies to Windows and other operating systems. But you need you need an HSA capable Linux kernel, which you can also grab from AMD repository at GitHub. Problem with that repository is that on Wednesday they released a new kernel with new drivers and new functionality, but they only packaged it for Ubuntu. So if you want to use something different or better than Ubuntu, for example, like OpenSUSE Tumbleweed, we have managed to extract all the important pieces and build ourselves an RPM that you can get from our build service at the address below. Then what you need to do is that you need to compile your own compiler. I'll go very briefly through this as well, because it's really not complicated and nothing to be afraid of. I still recommend at least a brief look at the documentation of building GCC that you can find on the GCC website. But what really happens is once you have the source, you need to get prerequisites, which are libraries for dealing with big numbers, complex numbers, and so forth. But if you do not want to use your package manager of your Linux distribution, you can just execute this script, and it will download everything at the appropriate place. Then what I do is that I usually build in a special directory. Then you configure with not just these two options, but these are two options that are going to turn HSA optimization and offloading on. So there is an enable offload targets option that serves not only to enable HSA, but also other optimizations. And you need to provide a path to HSA runtime so that it can find especially the headers there. And then you just run make install, and you will get your own compiler in the directory where you configure it, for which you configure it to. Once you have it, you get your example that you want to play with, compile with FO OpenMP, and when you want to run it, you need to set the LD library path so that all the necessary libraries, which means the libgomp, the OpenMP runtime from the branch, and the HSA runtime can be found. Now, there is one key difference between support for HSA and support for other accelerators in GCC, and that is that the teams that were working on other accelerators, which means NVIDIA and Intel MIC accelerators, they have chosen to force the users, or make the users, or distribute to the users two different compilers, one for the host and one for the actual device, one for the accelerator. And then you have to use the more complex syntax of the enable offload target to tell one compiler about the other. Unlike other compilers, we did not do this. We are able to produce code for HSA, the HSAL, from one binary. That has a few disadvantages, but we do believe that the advantages overweight them. So once you have this compiler, what will happen? The compiler will attempt to compile each target construct and each function with it declared target construct into HSAL. I said attempt because for various reasons that I will describe, it may not succeed. But we have shared virtual address space, as I said before, which means two things. I've already mentioned one, and that is we can ignore the mapping clauses and we don't really have to worry about target data and target update because the whole APU, both the GPU part and the CPU part, has cache coherent, albeit with a bit relaxed consistency, but cache coherent nevertheless view of the memory, and they use the same addresses, even the same pointers. But it also means one other important thing that devices which do not have shared memory do not enjoy. And that is when a particular kernel, for one reason or another, cannot really be compiled for a GPU, either because it is impossible, because it makes sense, or because our compiler is just not yet capable enough, we can always just not emit code for that kernel and fall back on CPU implementation. Now, this gets a little bit more difficult with failed functions. Nevertheless, because, and I will talk about it a little bit, we should be able to figure out which kernels can actually be run safely and which cannot. But the important thing is that because because we do have the shared memory and the unified view of the memory, it is possible that one target pragma is compiled for a GPU and does changes in the same memory, and then these changes, even without any interleaving target update, for example, are picked up by a CPU kernel, which the user originally intended also to be compiled on the accelerator, but it did not succeed. But let's talk about the things. One more thing. And in any way, and this is a feature of all of the acceleration scheme of GCC in general, the runtime is, of course, the thing that decides whether and to which device, if you have more to offload. So if somebody had both an HSA processor and Intel MIC accelerator, you could decide using, for example, an environment variable to what accelerator you want to send your code. But so let's have a look at what we can accelerate and how. So of course we are able to accelerate the very simple loops. This loop is taken from the stream benchmark. It is, as you can see, a simple vector copy. And the only modification that we've done to it is that we added pragma OMP target. Now, because we have not added any mapping clauses, this might not actually be a portable code. Nevertheless, it works on HSA, and our GPUs can pick up the same addresses. We do not attempt to do any address translation whatsoever because we don't have to, and it just works. However, the difficulties start elsewhere, and mainly from the explicitly parallel GPU programming model. Because you can compile this example in two ways. In one way, you can compile the example just as the specification tells you to. So you run one thread that would run the body of OMP target. That OMP target would then use dynamic parallelism to spawn a number of threads to run the body of the OMP parallel. And then the pragma construct would divide the iteration space in between that number of threads. And there would be an artificial loop for each thread, where each thread would loop over its portion of the iteration space. And that would work out of the box mostly, just with HSAL backend. But the problem is that it is not efficient. What we wanted to produce for a GPU would be an explicit grid, so that when we call the target, we would provide the grid parameters, the grid size. We would actually say this is a 1D grid, and its size is stream array size. So let's say 16 kilo, 16 kilos of, the arrays have 16 kilo elements. And we would not ideally want to have any control flow, any looping, any artificial loops if we wanted to run this on a GPU. So we have changed the expansion of OpenMP in GCC to do exactly this and actually copy the code very early and then process it differently even throughout the OMP lowering and expansion. And let me show you the results. This is the first loop. There are 3 more. There is a there's a loop doing scaling of the whole array. There is a loop that adds 2 huge arrays together. And the final one, called triad, does both scaling and addition. And these were the results. So we have this APU, which we got in the spring. It is an AMD engineering sample, so I'm not allowed to say much more about it. But this is the measurements we got when we used the current version of GCC on the CPUs. And it is, including vectorization, it is at the highest optimization level possible. The processor, the APU, or the CPU in the APU is not a particularly strong one, but it is, the results are better, for example, than on my notebook, which is 1 year old, and I consider it very, very nice. So it's not a bad machine. So these are the results for 64 kilobytes of memory. This is 16 kilos of float on a Carrizo APU. When we run the CPU code, this is when we run when we run the code on GPU and we actually expand it especially for GPU. So what we say, for lack of a better word, is that we gridified the loop. We have turned it into one call into the HSA runtime, giving it the kernel without any looping construct, representing the OMP4 construct, and the throughput is very, very nice. When we just use the CPU intermediate, when we just use the CPU expansion of OpenMP into GCC intermediate language, and then just translated this GCC intermediate language into HSAIL and ran it on the GPU, the performance was very, very poor. So the bottom line was really we probably need to handle code for GPUs differently very, very early on, and that gratification is a very, very worthwhile go. Now, if you are familiar with the stream benchmark, it says in its README file that in order to get, how to put it, in order to get representative results, you should run it on much bigger arrays. So this is a fairer comparison of the GPU and CPU when it comes to the throughput that you can get. Nevertheless, the traditional expansion is even worse in comparison. And because over here the bars are almost invisible, that is the reason why I actually added the previous slide to the presentation. But the gratification requires a little bit different way of thinking about OpenMP. You no longer have the luxury of reasoning about each construct in isolation. When you want to gridify this loop, you have to gridify the whole thing, and which means that each clause of each construct is a clause affecting the whole grid. It also means, for example, that the iteration space size over here from 0 to stream array size is not only property of the for construct, but it is also the property of the target construct, because it needs to be passed to HSA runtime so that it can prepare to run that many threads. Which, by the way, brings me to the previous presentation and the idea of whether it was wise to leave implementation defined defaults in the target in the target environments. Well, over here, if the stream array size is 16 kilo, that is the number of threads that the runtime will pretend to generate. They will be a very lightweight GPU threads. Nevertheless, if you asked inside the body of that loop, give me the number of threads, you would get 16,000, which is unlikely on a CPU. And of course, if your programming techniques involve such things as creating an array of the size of the number of threads, then you are in dire trouble. So it does change. So the changes, although they seem to be very straightforward in the beginning, there are very, very many implications. Now, one of the implication is that perfect construct nesting is required. In order to do gratification, at the moment, the compiler can't do it if there are any statements in between the target and parallel, or in between the parallel and the for construct, because it is fairly different to reason about that. The problem is with the current implementation that the perfect nesting is required at the intermediate language level, which is a problem because especially the Fortran, but not only, but especially the Fortran front end, often puts statements in between them, even when the programmer did not put any there. So this requirement will have to be relaxed somewhat, and we will be working to that. In one way, it is also similar to vectorization, so that at least in the early stages, what we believe is that we will be giving feedback to the programmer why we did not gratify a particular target construct containing a loop, and hope that we will be able to provide enough information so that the programmer can change their code to get it gratified. But there are things that prevent gratification. For example, if you specify a maximum number of threads, then there is a maximum number of threads, and the threads have to loop. So that prevents gratification, as does non-automatic loop scheduling. If you say you want a chunk of, especially when you provide a chunk size, if you say you want a particular chunk size, then for various reasons, the implementation has to honor that and cannot change the behavior. We do have a limited support for teams and distribution constructs, though. Nevertheless, we, for example, do not allow to limit in any meaningful way the maximum number of teams. So you can give a maximum number of threads in one thread group, but that's pretty much all that we allow at the moment. This will have to be expanded a little bit. I have almost finished support for reductions through atomics. Of course, on a GPU, reductions should be ideally done using recursive implementation. Nevertheless, that is something for the next release. But we do want to support them in the source code, so we will have them in the first version at least implemented at least using atomics. And we want to support collapse 2 and collapse 3. Now that doesn't mean that when you specify collapse 27, the code will not compile. It will just not get gratified because, of course, collapse 1, 2, and 3 can map very nicely to the 1, 2, or 3-dimensional grid that HSA supports. If you want more dimensions, some looping is necessary, and therefore looping will be required. But there are things that actually prevent your code from compilation. And first, an important thing, and that I think will actually never really work because it will never probably really make sense to compile it for GPU, is that anything that looks remotely as a critical section. Because only, if you remember the slide with the teams, only the threads within the thread group, within a work group, can actually communicate and synchronize, and it is so difficult to try to implement critical section that would span work groups that it's just probably not worth it. There are things that we do not intend to support now. We have not really even thought about sections and tasks and other non-loopy work sharing constructs. Although HSA has support for queuing kernels and actually specifying dependencies among them. So in the future, we may or will probably want to have a look at whether OMP tasking constructs can be mapped into this programming model, but so far we have not gone that far at all. Similarly, we have not really thought about supporting SIMD constructs. There are two reasons for that. One is architectural within GCC, because, and this is the disadvantage of doing everything within one binary, because the vectorizer, of course, currently is parameterized to vectorize for the CPU. We need to, we actually have to be able to we actually have to allow it to reparameterize itself either for the CPU, either for the host, or for the accelerator. And architecturally within GCC, this is not a simple thing. Nevertheless, it's certainly doable. Another task is that often we will be partitioning a straight line of code. And when we do that, when you vectorize a loop, what you end up with is a loop with fewer iterations. Over here, we do not have a loop. We will have to reduce the grid size, which means that it will be, because of architectural reasons, and interprocedural optimizations and so forth. So it is also something quite difficult. We do not support things like dynamic scheduling when the loop would have to call back to the runtime, because if 64 threads that work in lockstep all wanted to request another chunk from the runtime on the CPU, that would be just, probably just not worth implementing. And let me actually hide this. And this list of OpenMP features that we are currently not able to support and we might have problems supporting even in the long term is not complete. I mean, it is an overview of things that I've come across and I could immediately think of when I wanted to put down a list of things that I see as very difficult to support. But there are problems beyond OpenMP, and that is that HSA cannot do well a few other things. One very obvious thing that it cannot do well are indirect calls. It is actually, the standard provides some support for it, but the runtime and the CPU has to do a very heavy lifting to allow one single indirect call. And I don't believe it is actually even implemented in the current runtime. And it is just really a difficult thing to do. But that, of course, brings one, one conclusion from this slide is that when you look at the first and the last item, and if you, I don't know about other implementations of OpenMP, but at least the GCC runtime support of OpenMP programs, the libcomp, it is based on indirect calls and critical sections and mutexes. So we really try to implement almost everything in the compiled code, and we have to rely very, very little on support from the runtime, which is, again, very different approach from how CPUs, how OpenMP has been compiled and how it's been processed. Oh, so I've actually been fairly quick. So what I wanted to tell you in my talk is to bring your attention to HSA and its unified virtual memory, and not only that it allows you not to care very much about the mapping, but also to be able to compile only some target constructs for GPU and not others without caring for updating the memory in between. And I wanted to communicate to you that HSA is about to be programmable with GCC through OpenMP constructs, and we are primarily targeting OpenMP constructs with the emphasis on portability. We don't care about the mapping constructs. Someone else has to add them in there, but we do not. We know that it is important that people should write the same code that would run anywhere and hopefully run well anywhere. I've already told you that fallback on CPU implementation is a crucial feature that allows us to go forward in the initial stages, and in code that relies on indirect calls or critical sections, it might be the thing that will allow us it might be the feature that will allow us to compile that code in the long term as well. And also wanted to stress that what we believe is an important concept of compiling OpenMP code for GPUs is the gratification and code duplication, which means that even though that the code will be duplicated very early on, and for example, and it will work best if, for example, the parallel for constructs are allowed to do their own thing. So that various clauses that, for example, specify the scheduling are very alien to efficient compilation for GPU. And of course, the gratification as a concept is the holy grail, what we would like to do with pretty much any loop that is supposed to be parallelized and offloaded. And 5 minutes at least, if not more, faster than I thought it would be. Nevertheless, if you got any questions, we got a lot of time for them.
Is there any runtime at all on the GPU?
Currently, no. We need them.
You don't need to, well.
No, we need it. We need it. The reason why we need it are math functions.
Not any bookkeeping or thread creation. I mean, that's all done by the hardware, or by the generator.
That's all done by the hardware. But, well, let me go back to the parallel loop, this one. If you do not gratify it, what you need to do is to use dynamic parallelism to run another kernel. So if you switch off parallelization, or if you write this code, but for the fun of it, you add static that is compilable for HSA, but will not be gratified. And that will mean that yeah, you will get only one thread running the target thing, and that one thread knows how to invoke another kernel. But that is, again, something that is code generated by the compiler. Yeah, we do expect that a lot of the support patterns will be generated by the compiler and not provided by the runtime. But there will be a small runtime. There will be, but not for much bookkeeping and these things.
How about I/O?
I/O.
From the device. Printf.
Yeah, currently it doesn't work. What is possible and how we plan to support something like, how we support I/O, so we support some limited printf, is that HSA has mechanisms of GPU invoking code on CPU. So it is slow, of course, but it works pretty much in the same way that dynamic parallelism works. So you create a packet and you throw it on a queue that the hardware is able to manage, and then the CPU hook will be able to collect that packet, look at it, unpack it, and do a printf. So no, it currently does not work because for our debugging purposes, we've just managed to do without it, but I do understand it's interesting and doable, and we will have it. You are, of course, right.
Codes have calls between the parallel and the forward. What are you going to do when you want to support that?
There are three reasons basically why the kernels that are not gratified are slow. Yeah, that's probably the one thing that I forgot about. The one is control flow. GPUs do not really like control flow, but as long as all of them go one way or the other, the control flow should be okay. Another thing is the dynamic parallelism. We have seen actually quite important slowdowns. We hope that the HSA runtime is able to limit these somewhat. And the third reason why even this toy example is slow is how the iteration space is divided among threads, and we believe that is the biggest problem. The way how the iteration space is divided among threads is aimed at achieving the best performance with CPU caches. So each thread gets a contiguous chunk of the iteration space, and it works on the elements of when it uses those indices as indices into arrays, that allows for cache locality and good cache performance. But that is exactly what you do not want to do on a GPU. One important feature of GPUs that allows them to achieve the performance is that they are able to coalesce memory reads and writes. And when you do this, it is not possible because when they work in a lockstep and each thread has its own contiguous chunk, then each access is very far from the other. So we not only want to do code duplication and different expansion for the sake of gratification, but when there is looping construct, we would actually want, and no scheduling clause, what we want to do, and what we do believe will help a lot once the dynamic parallelism overhead diminishes somewhat, is that we will just do different distribution of the loop. We also do not have, I don't know, as we talked about it, because OpenMP currently does not have any support for the group local memory, or at least I really couldn't find any. That basically prevents tiling, which I believe is another very important programming technique when programming GPUs. But I'm the implementation guy, so yeah, I'm very glad that's not my fault. Yeah. But of course, once that is specified, we will take that into account. And of course, then the distribute and teams constructs will become much more useful. At the moment, I just do not want to, the support is really just so that the gratification is not prevented in simple cases.
So when you say GPUs, you mean?
When I say GPUs, I mean HSA GPUs. So at the moment, that's, I believe, AMD only. But we will see.
You could run it. You could generate something or make it run it.
And you're going to support HSA?
That's why I asked the question, because NVIDIA has the same architecture. You can gratify it where you want it as multi-dimensional. We would never limit to just parallel 4. Teams map onto what OpenACC call games. You get SMX assigned to you for that team. Then criticals work, because criticals are on something that can synchronize. So criticals doesn't get thrown away, for example. Parallel works inside of it, so now you can actually do, and then your vectorization occurs within the parallel. That just maps down your 3 levels of parallels. Admittedly, that's an architecture that allows you to look that way. The way AMD's architecture looks is a little less hierarchical. It's more just get rid of vectors.
Yeah.
And you're basically saying you want to vectorize this entire. You call it gratify, it's really vectorization. Yeah, that's the problem. To me, everything's a vector.
Okay. For me, everything is parallelization, but yeah, you usually do not refer to parallelization of the outer loops as vectorization. But yeah, I mean, of course, the problem is very similar.
It'll be interesting when you finally get to the point of supporting calls, multidimensional loops that you can't collapse. You can't, because you can't see them. You have a loop, there's a call in it, you have another call, you have another call, and you actually make another level of build. And that's the type of codes that are really out there and really need to form.
Well, when a lot of testing has been done by AMD people who have actually tried this on scientific benchmarks that are out there. Okay, but yeah, this is a preliminary work. I mean, yeah, I'm not gonna pretend that. Yeah, sure. I'm not gonna pretend that this is not work in progress, and it is.
That's fine. Just into the real world, you start seeing the wild codes that users throw at you, and they want them to run quickly. And you're trying to compete against the Xeon 5, which is an incredible processor because it does exactly what it claims to do. It runs everything in parallel, just like it's a big parallel machine. And now when the GPUs come along, we have restrictions on what we can do well. And we have the same basic clock capability, but the programming of the two machines is very different. And
Yeah.
as you start putting constraints on what you allow your GPU to do, you start falling behind what Intel has. And the goal really is to be better than Intel, not worse.
I'm afraid that, being better, what does it mean? I'm afraid that being more versatile, allowing for, critical sections, which Xeon arguably is able to support, is going to be almost impossible. Supporting, yeah, but then that would.
You're supporting within a.
As long as you stay within
a world.
Actually, no, just stay within SMX. So gain,
But yeah, of course, the goal is to just run the same code that does not have too much of synchronization in it, and
convince everybody to get rid of synchronization. Everybody runs faster. Any real questions on the manufacturing?
So I have a mechanical question. So where does the
sorry?
The GCC compilation code that embeds the input code in the
Oh, how it works?
link time that re-optimizes it for the given target?
No, the Finalizer is, as far as I know, actually LLVM based. And at least with the old runtime, the previous, before Wednesday, the previous one.
Like password, where do you put the HSAL codes on that?
Where I put your HSAL code. HSAL has two representations. One is textual, another is binary. They are almost equivalent. You can have comments in the binary representation, and we put it into an ELF section of its own. What actually happens is that when you have, when the compiler produces some HSA kernel, it also produces a static initialization constructor, static constructor for the compilation unit where you have the kernel. And that static constructor registers the brig, the HSAL code, with libgump, with the runtime support for OpenMP. When that compilation unit is loaded, so either at application start or when you open it dynamically. And only then, when you run for the first time a target pragma, the CPU code will call into libgump. Libgump will decide whether to parallelize or not. If it decides to parallelize on HSA, it will load an HSA plugin. The plugin will find, what does this code, or where is the implementation of this code for HSA? It will finalize it. It will finalize the whole thing, but then it will also locate it. And then it will use the HSA runtime provided by AMD to actually run the kernel.
So it's the finalizer that is HSAL, right?
Input to the finalizer is break, yeah, but that's really just a binary representation of HSAL.
So when you generate that stuff, code generation time, at the same time you're generating Intel code for the code
Yeah.
or whatever, right?
Yeah.
Somewhere in the code generator you switch and say, I'm going to generate this other stuff.
Basically, yeah. Basically, we clone. At one point in the compilation process, of the bodies of almost all the target and parallel constructs, at least, are represented as a function of its own. The code in the body is outlined to a special function, and then that function is, if we want to compile really the same stuff, if we do not gridify, for example, that function is duplicated and then goes through the optimization pipeline with a special mark, if it is for HSA GPU, as this is a HSA GPU thing, for example, switch off factorization. But it doesn't switch off almost any other optimization. No, it doesn't. And then such function is not even output into the x86 assembly. It is only expanded as HSAL code into the break section. But it is linked with the CPU implementation because everything has a CPU implementation. The CPU implementation is always compile.
So you think that's seems like too much time for you actually think about things.
No problem, no problem.
Do you think that's that could be? You said earlier that's it's better than having two compilers, but now you're gonna have one compiler, but you have to tailor it in different spots with two different architectures. Maybe it doesn't matter because the grade or HSAL or whatever you want to call it so high level that you're not really specializing.
Do you mean why the other teams decided to have two compilers? Whether
Yeah, I'm just comparing the two.
Sure.
You have one compiler. You're going to identify a function that's going to be targeted to the GPU, so you're going to do some different things for it for code generation.
Yeah, I think that, well, we at SUSE do not like this approach. We think it is a mistake. We think they are misusing, intermediate code streaming that was invented for a different purpose. It was invented for link time optimization. That is, for example, why they stream it at the same spot where LTO does. So we do not think that was a good idea. Nevertheless, the first people who did it were Intel, the team implementing the Intel Xeon acceleration. And for them, this must have been the easiest thing, because what they really wanted are two x86 64 compilers, just parameterized differently, different vector sizes, different. So yeah, they saw this as the easiest option and just did that. And for them, I understand it makes sense. For NVIDIA guys, yeah, they just followed suit. They just were told this is how it's being done, and they just did it. And it has certain advantages, and the work has been done. The streaming work has been done. So it might have been easier for them as well. Nevertheless, when we had a look at what optimization passes would need to be reparametrized drastically differently, we didn't find that many. It's vectorizer, because the HSA may not be able to, currently it only supports 128-bit vector instructions, so if the CPU supported more, we would have very big problems dealing with that GIMP input. And then of course the inliner, because we want to inline like crazy into GPU kernels, unlike into CPU functions. Because if you inline like crazy and try to link time optimize Firefox, your memory RAM, you will run out of RAM very, very quickly, for example. And that's really it. Those are the two important passes that need to be reparametrized. I mean, there is a few other passes that use 1 or 2 parameters, but that's not really that crucial. Thank you very much.